Hello and welcome to this video from the Corcoran Codex, which looks at big and critical ideas in the world of global finance. And what I want to do in this video is look at the idea of quantifying tail risk, one of the harder concepts in risk management, by using power laws. Some of the discussion has been inspired by the work of John Hull, and I'm going to walk through the idea of how we can make more sense of the kinds of events that occur infrequently but with considerable severity and use those in our risk modeling techniques. So insights about power laws observable in outlier values in financial data can provide enhanced quantification of tail risk. It can enable us to make more reliable estimations as to the likelihood and severity of outlier events. Power laws are evident for many variables in finance, as well as the size of cities. Some work has been done here to show that there is a kind of power law scaling with regard to the size in terms of population of many of the world's big cities. The number of visits to a website. Again, research has shown that there is a power law scaling evident there, and income and wealth distribution as well. So the simplest form of this power law relationship can be seen here. The value of a variable v, let us say, has the property that when the magnitude x of v is large, then the probability that v will exceed x equals this value k multiplied by x, and then we have the exponent here, a negative exponent. That in many ways is the key variable here, which effectively is the power relationship governing this overall equation. Let me give an example of where power law scaling is in evidence. So we're going to think about the frequency and magnitude of earthquakes. Statistics on global earthquakes are maintained by the US Geological Survey, USGS, and are being constantly updated. They keep a database of all earthquakes around the globe, and it is being constantly updated. The USGS estimates that several million earthquakes occur in the world each year. But many of those go undetected because they hit remote areas or have very small magnitudes. The magnitude of earthquakes, according to the USGS, can be stratified in terms of their descriptors from great to very minor. The frequency of an earthquake of a particular magnitude, which is measured on the logarithmic Richter scale, is inversely proportional to its magnitude. A simpler way of saying the same thing is that smaller earthquakes occur more frequently than larger earthquakes. But it is possible to be more precise about the nature of this inverse proportionality. There is a mathematical function which describes the relationship between the magnitude and the frequency. The equation has the form of a power law. So I'm going to show some data now from a study by the USGS from some time ago, but the evidence is that this kind of pattern is persistent. So we can think in terms of the frequency of occurrence of earthquakes. You remember I mentioned they have this idea that the USGS uses a descriptor here. Then we can see this in terms of, say, the value on the Richter scale, which, bear in mind, is logarithmic. So, for example, a great earthquake, according to the USGS, which has a magnitude of 8 or higher, on average, this would occur once per year. And a major, let's say, this is the next strata down, is an earthquake with a magnitude between 7 and 7.9. And according to the USGS, these occur on average roughly 17 times per year. We have this category, 134 times a year, moderate, which is in the interval between 5 and 5.9, 1,300, and this one has a likelihood of occurring roughly 13,000 times per year, and so on. Now, I think it should be even evident now that when we look down this column here, that as we move down, especially from here down to the bottom, there is an increase of roughly 10 times. Now, when we think back to this column, which is the magnitude, this is a logarithmic scale. So the way to think about that is, let's say that this is a 6.9 earthquake on the Richter scale. This happens to be 10 times less powerful than this particular quake here, which has a magnitude of 7.9. So this is a logarithmic scaling, which as we descend, the strength, if you like, of the earthquake is declining by 10 times as we move our way down this column. Let's say we do something quite interesting, which is take that data we just looked at and plot it on this graphic here. So now on the horizontal axis, we have the magnitude of these quakes, which, as I just said, is according to the logarithmic Richter scale. And let's say we then focus on the vertical axis here. We keep here natural numbers. We don't use logarithmic numbers. And we can see here, for example, this would be the idea of a magnitude 3 quake. And if you look back at the last slide, it would tell us this happens about 130,000 times per year, or quakes of that magnitude occur about 130,000 times a year. We plot all the points, we come down, we end up with this curve shape. Now, but something very interesting happens if we keep the horizontal scale according to the Richter scale, which we know to be logarithmic. But now we think of the vertical scale once again, using the same numbers that we used over here, but now expressing them according to their natural logarithm. What we find now when we join up the points is something very interesting. The relationship, this line here is a straight line, and that is very strong evidence of a power law relationship. What I want to do next is turn to some very interesting work by John Hull that I mentioned earlier on, where he talks about using power laws with regard to better ways of thinking about quantification of extreme losses, tail risk, etc. Hull has a section in one of his books where he uses data he observed from the size of daily moves in the foreign exchange markets. And what he shows is that the percentage of days when the absolute size of daily FX moves is greater than expected if the data was normally distributed. And we know, because we've looked at this elsewhere, that very often financial data is not properly describable according to the standard normal distribution. So let me explain what Hull has done here. So we have here these different Z values or Z values, which essentially are the number of standard deviations away from the mean. And we can use the Excel function equals norms dist, plug in the Z value, these values in this column, to calculate the area under the bell curve, in other words, where we are assuming the data is normally distributed. And this gives us the area under the bell curve to the left of the respective Z or Z value. So, for example, if we use the Excel function, this one here, plug in 1, we get this value returned to us, 84%, 84.13%. And if we subtract that from 100%, we get that number. And we are considering both positive and negative moves away from the mean, so we need to double it. And what we find is that using that same basic logic, but not referring back to the normal distribution from the actual observed empirical data, Hull shows that in fact in the FX market, this type of move happens 25% of the time, unlike the 31 or 32% that's over here. And we can see as we work our way down, we use the same idea. We take the Z value, plug it into this function, we subtract from 100%, etc. And we then double the results, but then we compare them to the observed data from Hull's work. So what the norms dist function does is to find the total area at or below, in this case, one standard deviation. combine the regions under the normal distribution curved from left to right. So we know that below the mean, since the normal distribution is symmetrical, we have 50%. Between the mean and one standard deviation, we have 34.13%. And if we add those together, we get this number here, the 84.13, which is exactly what the norms dist function has returned to us. What this means in simple terms is that only roughly 16% of the data lies above plus one standard deviation from the mean. That number there, which, as I say, is the value returned by this function. Hull shows that the observations for greater than 3 standard deviation is this number here, 1.34%. But according to the normal distribution, with that SD value, it should only be 0.27 of the total observations. How do we get the expected value for the appropriate sigma? Well, we just looked at that. We can use the Excel function, enter 3, and this gives us the result of 0.99865, which is equivalent to 99.87%. So if we subtract that from 100%, we get the number of 0.134. Since we're considering absolute changes, in other words, both sides of the mean, we can double this, and that gives us the result of 0.27, which of course is shown here. Hull's data shows that at this 3 SD level, the occurrences exceed the expected value from the bell curve by more than 6 times. 1.34 divided by 0.27. There's quite a bit going on here, so let me take my time to walk through this. So once again, we can see the same data that we just looked at. So we have the observed, the 1.34 we just talked about. Bearing in mind that there are both positive and negative values here, we take this observation, which comes from Hull's data, divide by 2. This gives us this column here. The next thing we want to do now is to apply the idea of using logarithmic charting and seeing what the relationship in graphical terms looks like when we are using natural logs for the data. So we take these two columns here, and we then apply the natural logarithm based on this column for this data, this column here for the z value or z value, and we then create the plot, which we can see here and can be clearly seen in the Excel file. Now, what we want to do next is, let's say, focus on the right-hand side chart, where we're going to look at the outliers where the standard deviation is greater than or equal to 3. So effectively, we're going to look at just these values from 3 standard deviations down to 6. And we can see when we plot just those, not the whole set of data here, but just those that I just mentioned, we get this much clearer straight line relationship, which, as I have said before, is clear evidence that there is a power law in effect here. The next thing that we can do is to perform a linear regression of the values on the right-hand chart, and we can see that Excel will show us this, that the equation of the line of best fit here, is y equals negative 5.5x plus this constant value here. This represents the gradient or slope of this, which of course is downward sloping with a negative value. This is what is known as the y-intercept. The next thing that we can do is to say, well, the exponent then of the power law for this data is simply the gradient, the negative gradient, the negative 5.5. And if we take the anti-log of the intercept value, which is this, we have a constant k value of 2.88. So that is what we've been able to derive from just looking at the extreme or outlier values, doing the linear regression in the manner that I've said, and we now have what we need for the power law. So let's say we want to calculate the probability for a 7.5, just hypothetically chosen, sigma or standard deviation occurrence. Again, in absolute terms, we can simply plug this into the formula, the one we looked at earlier, k multiplied by 7.5, raised to the power of the alpha, which is negative 5.5, times 2. This tells us that the likelihood or probability of a 7.5 standard deviation move is this amount here, which enables us to go on and have far more data to think about when we're looking at the distribution of losses, because it allows us to have a reliable estimate as to what the likelihood of what in effect would be an extreme loss, 7.5 standard deviation away from the mean. Just to generalize the power law for outliers, which is what John Hull does in his book, let's say we have an analysis that suggests an alpha value of 3 is discernible as the power law exponent in the outlier behavior of a financial variable V. So I'm literally quoting from his book now. Suppose that we have observed that the probability that V is greater than 10, for example, is 5%. Then solving for K, we would have the following. 0.05 equals K times 10 to the minus 3, that's the exponent. Therefore, simply rearranging that, we find that K equals 50. This would then enable us to determine that the probability, let's say that V is greater than 20, is as follows. So we have the 50 value, we now have the 20. So we take 50 times 20 to the negative 3 exponent, and that resolves to this number here. And that example is taken from John Hull's book that I have mentioned previously. So I hope very much that you enjoyed that video and found it interesting and useful. If you find this type of material to be of value to you, where I analyze critical ideas and episodes in the world of global finance, could I strongly suggest that you decide to subscribe to this channel. Thanks very much for watching.